All right, looks like we are live. Let me know in the chat if you can hear me. Put a plus in the chat if you can hear me. Hopefully you can. If you can't, I'm just talking nonsense to myself here in my own world. No pluses in the chat yet, so I'm a little nervous. Hopefully you can hear me. My mic is on. Any returning or new students in the chat today? Wondering if there are any new ones. You're in the right place if you're here for the free live lesson, Algebra 2. Today we're going to be talking about logarithmic properties. Returning, wow, Daniel, welcome back. I noticed you changed your profile picture. I almost didn't recognize you. Welcome back, Daniel. Can't believe you're here for Algebra 2 as well. Well, welcome back. Love that you can hear me. Awesome. Well, yeah, so today we're talking about Algebra 2, logarithmic properties. Super excited to share what I have planned for you today. New student, Olivia, welcome. Welcome, welcome. In the description, in the video description, you will find a professionally designed workbook to help you follow along in today's lesson. With every lesson, you will get one of these workbooks so that you don't have to, frantically be jotting down all the problems. They're already there for you in the workbook, so you can load those up on your iPad or you can print them out really quick. And so before we begin, I want to make sure that everyone who can possibly benefit from today's stream will join today's stream. So if you have a friend, family members, group chats, you think anyone would benefit from tonight's stream today on logarithmic properties, go ahead, copy that URL and send it over before I introduce myself. Raymond's here to mod for us tonight. Hi, Raymond. Welcome, welcome. Yes, Raymond is the best mod, my favorite mod. Thank you for being here, Raymond. If you have any questions, Raymond will be answering any questions that do not pertain to today's lesson. Raymond will try to answer them, or if it's inappropriate for the lesson, Raymond will be the one tagging those. Thank you, Raymond, again. All right, so a little bit about me. I'm Eddie. I'm the senior math teacher at my EdSpace. I've been teaching for 9 years in high schools, colleges. I've private tutored every level from 6th grade math all the way to students preparing for graduate school. So I've taught over 2,000 students. And yeah, I did really well in school. I got all A's in my math courses, got a perfect score on the SAT, got into my dream school, UCLA. Go Bruins. And after graduating from UCLA with a degree in pure mathematics, I decided to go into teaching right away. I found really quickly that I love teaching math. And I've also found out really quickly that I'm pretty good at it because a lot of my students got into the top universities in the nation. They got 5s on their AP exams, 800s on their SAT math, exceeded the standard on, state, national exams, whatever it may be, always performing above the national average. But most importantly, I knew that I was having fun because my students were having fun. And that's what math should be, right? Learning math should be fun, and that's what we're here for today. I'm here to show you that math can be fun and approachable to make you the next generation of math geniuses. Okay? All right, so without further ado, let us get started. I love starting off my lessons with a vibe check. So what do you think these images have in common, or how are they different? I'm going to go through each image, but while I go through them, don't be shy. You can message me in the chat what you think these images have in common or how they're different. There are no wrong answers. It's just based on your observation, right? We did do this before, Daniel. Yes, this is the same live lesson from last week. And I know you've been joining for a lot of these different subjects as well. So, I mean, you're going to be an expert at this today. Yeah, so the first image on my left of the screen is a pH test. It's to test the acidity of any liquid, of any material. Yes, the questions will be the same as well. The middle image here looks like the image of a star, right? It looks like the image of a star. Maybe the brightness of the star is what we're measuring here. On the top right, we see a decibel scale. So how loud things can be, how loud a sound can be. And on the bottom right, I see something called a Richter scale. This is a scale that measures the magnitude of an earthquake or any tectonic plate shifts. So what do you think these images have in common, or how are they different? In the chat, let me know. Some things that I've heard from students so far in my previous live lessons were the colors. Only 2 of them have a wider range of colors. It's the pH test and the decibel scale, right, for volume. Some have said, only 3 of them look like they're part of a graph. The stars, the picture of the image of the star just looks like it's just there. Yeah, charts, right? They look like they're in the form of a chart. But the main idea here is that all of these use logarithms. All of these use logarithms. Testing the acidity of any liquid or material, the brightness of a star, luminosity, otherwise known as, all are measuring something. Exactly, Kanav. Great input. Measuring the level of sound, measuring the magnitude of an earthquake. Yes, all of these we can measure using logarithms. And that's what we're talking about today. So I love also starting off my lessons with an APK. I usually start off my lessons with an APK just to get our brains running, our gears flowing. Accessing prior knowledge is what APK stands for. So fun fact, despite popular belief, logarithms were developed before the formal notation for exponents to convert multiplication and division into simpler addition and subtraction. It was only later that the connection between logarithms and exponents were made as inverse functions, which is really interesting because when we learn addition, we learn subtraction right away because that's the inverse function or inverse operation of addition. Same with multiplication and division. Same with square roots and powers. But with logarithms and exponents were kind of discovered separately, right? Discovered and developed separately, and later on, boom, came together. So let's take a look at how to write a logarithmic equation. But before we start, how many of you have seen a logarithm before? Put a Y in the chat if you've seen a logarithm before, and put an N in the chat if you have never seen a logarithm before. Y if you've seen a logarithm before, N if you have never seen a logarithm before. And if you're answering N today, that's going to make me even more excited because you're going to learn so much today. And by the end of today's lesson, you're going to feel so smart. You're going to feel like you actually understand logarithms. IJ, Olivia knows, amazing. It's very excited to show you guys logarithms today. You're going to learn so much today. You're going to be way ahead of your classmates once you get to this topic in Algebra 2, and they're gonna love you for helping them. All right, so if 3 squared is equal to 9, we know that for a fact. 3 squared is 3 times 3 equal to 9. Then log base 3 of 9 is 2. So that's how we verbalize it right here. Log base 3 of 9 is 2. In other words, what we're asking when we're converting exponential equations to logarithmic equations, we are asking b, the base, to what power p gives us a, the argument of the log. So again, a stands for the argument of the logarithm or answer to the exponent. B stands for the base of the logarithm or base of an exponent. And p stands for the power of an exponent. So b to what power p gives us a. That's how we can convert from logarithmic equations to exponential equations and vice versa. Okay, so this was our very first example. 3 squared is equal to 9. Notice how the 3, the base, is right here, base of the log. The 9 is the argument of the log, and the 2 is the power of that exponent. Okay. So again, the question we're going to be asking ourselves today whenever we see a logarithmic expression is b to what power gives us a? B to what power will give us a? So let's take a look at all of these problems without using a calculator, finding these values. The first couple I will model, and then I will start asking you to solve these in the chat with me. Okay, so this first one, we are asking ourselves 3 to what power will give us 81? 3 to what power gives us 81? Actually, let's try that in the chat. I feel like we could solve that together. 3 to what power will give us 81? In other words, 3 multiplied times itself, how many times will give us 81? We can rewrite this. So I'll put letter A right here. We'll start it off right here. 3 to what power gives us 81? This is equal to this box. What will this box equal? 3 to the power of 3 times 3 is 9, times another 3 is 27, times another 3 gives us 81, right? 27 times 3 is 81. Great, Olivia. 4 is correct. So the answer here is 4. Pretty simple, right? Starting off easy. Let's keep it moving. So log base 5 of 1 is equal to something. So in other words, 5 to what power is equal to 1? Now we have to think back to our exponential properties, right? Whenever we take something to what number power gives us 1? That number is, great Kanav, 0. Quick with it. 0 is correct. Log base 5 of 1 is equal to 0. So working with these logarithms, we have to think back to our exponential properties as well. Log base 7 of 1/7. So that means if this is equal to some box, 7 to what power gives us 1/7? Now this one's interesting because now the base of the exponent turns up in the denominator of a fraction, which means our power can no longer be positive. It must be negative. I see Kanav is really comfortable with their exponential properties. Awesome. -1 is correct. How about this next one then? 11 to what power gives us the square root of 11? This time, 11 is still in the numerator, so we're not going in negative powers here. We're sticking with positive values, but for our exponent this time, our power will be 1/2. Reminder that whenever we have something to the 1/2 power, for example, x, that's the same thing as rewriting it as the square root of x. If we had x to the 1/3 power, that would be the same thing as the cube root of x, so on and so forth. So again, accessing some prior knowledge of our exponential properties. E, what would this one be? 2 to what power gives us 1/8? So this time we know for a fact it will at least be negative, right? We know it will be negative. And 2 to what power gives us 8? Let me know in the chat. We have 2 to what power is equal to 1/8, so we know that will be negative since our number turns up in the denominator. 8 is a power of 2, and 2 to what power gives us 8? Don't be shy. Don't be shy. Don't be scared to make mistakes in the chat. You're not being graded on this, right? All you see is other students' usernames, so don't be shy. If you can make a mistake, that's awesome, because brain research shows that when you try something, you try something and you make a mistake and you fix that mistake, that's when learning really occurs. That's when you really retain the information. Otherwise, if you're just passively watching, you're not learning anything. It's kind of like when you take notes for an exam and you're trying to study the notes and you're just reading the notes. It's a waste of time. You actually have to try problems. You have to answer questions, right? You have to participate in order to really learn, right? So I'm really going to encourage you and push you all in the chat because I see that a lot of you are shy. Just, answer, right? Take a chance. Take that first step. That's the hardest part. And if you're wrong, who cares? You made a mistake. We're all learning this for the first time, right? -3, Olivia, is correct. Amazing, right? Because we know 2 to the 3rd power is 8. And because the power is negative, the 8 moves to the other side of the division bar. Amazing stuff. So now in F, we have 125 to what power will give us 5? So again, 125 to what power will give us 5? Well, this time, we know that our value 5 is still in the numerator, so we know that our power will be positive, right? We're not flipping to the other side of the division bar, so our power remains positive. However, our number is getting smaller, right? 125 to 5. Let's think about what happens there. 125 is a power of 5, right? We have 5 times 5 is 25, times another 5 is 125. So that's 3. But we don't want to put 3 here because that would mean we're multiplying 125 times 125 times 125. That doesn't make sense. Instead of a 3, we would write 1/3 because we are taking the cube root of 125 to get to 5. So in this case, we have 1/3 as our answer. And we're going to keep upping up the level here. 3 to what power gives us, this is the toughest one we've dealt with yet, this 1 over the square root of 27. So now we're combining a whole bunch of things. Give me some ideas as to what will definitely go as a part of this answer. What will be included as a part of this answer? Let's start with this. Will our answer be negative or positive? Put N for negative and P for positive in the chat. Will our answer here be positive or negative? Put P for positive and N for negative in the chat. We know, looking at our previous examples, right? You can use context clues here. The power here, does it have to be positive or negative here? Let's take a look. This 81 looks like it's in the numerator, right? There is no denominator here, so that's why this 4 is positive. 1 as well, 0, not negative. 1/7, however, because the 7 is in the denominator, we have a negative. 11 still in the numerator, so our answer is positive. 8 now in the denominator, so our answer is negative. 5 in the numerator, so our answer is positive. So let me ask again. 27 right here is in the denominator. So what does our power have to be? Positive or negative? I see Olivia put P. Anyone else? Any other responses in the chat? Kanav, IJ, anyone else? Will our answer here be positive or negative? Let's put a little note here to help us out as well. If we have any number x to, let's say, a negative power, that can be rewritten as that power in a positive form on the other side of the division bar. So that's how we know our answer here must be negative, since the 27 here is in the denominator. Now 3 to what power gives us 27? Well, 3 cubed gives us 27. However, we also have a square root, and a square root is 1/2. So we have negative 3 times 1/2, and if I were to write this out here, we would have negative 3 times the 1/2, and that will equal negative 3/2, and that would be our final answer. 3 to the power of negative 3/2 is 1 over radical 27. Okay, let's move on. H. Do we know any number, any power that we can take 9 to the power of to get a negative number? Let's see. 9 to the 0 power is 1, positive. 9 to the first power is 9. 9 to the second power is 81. We're only getting more positive. So that definitely doesn't work. If we go in the negative direction, 9 to the negative first power is 1/9. 9 to the negative second power is 1 over 81. Still not going in the negative direction. So is there an answer to H? H is actually what we call undefined. We are unable to define a logarithm with an argument that is negative, because whenever we have a positive base and we take it to any power, it will never equal a negative number, right? So that's why whenever you have a negative argument, the log expression will be undefined. Now, I, letter I, this one, we don't have a base, right? Look at all the other problems. We have a base, 3, 5, 7, 11, 2, 1, 25, 3, 9, but this one doesn't have a base. Whenever you are not given a base for the log, the base will automatically be 10. This is called the common logarithm because it's the most commonly used base for any logarithm. And 10 to what power gives us a million? Well, just count up the zeros. 1, 2, 3, 4, 5, 6. So we have 10 to the 6th power. And so our answer here for the log will be 6. And boom. We just solved a whole bunch of logarithms without using a calculator. Let's try a couple more. I kind of modeled through all of these because it is our first time seeing this. But let's take a look at some rules that we can use before we get into some more practice. So I'm going to prove the multiplication and power rule. So again, before in the APK, I mentioned that logarithms were first developed to make multiplication and division into simpler addition and subtraction. I'm going to show you how these work. So let's say for this product rule, let's say we set log base b of x equal to alpha and log base b of y equal to beta. I can rewrite these expressions as exponential expressions. B to the power of alpha is equal to x, and b to the power of beta is equal to y. Now notice what we're doing with x and y here. I'm multiplying. So if I multiply x and y, that's the same thing as b to the beta times b to the alpha times b to the beta. Using our exponential properties, if we have the same base and we're multiplying two exponents, we can add the powers. So bringing it up here, xy is equal to b to the power of alpha plus beta. From here, I can switch it back to logarithm form. I can take log base b, right? Base of the exponent is the base of the log. Our argument will be our resulting value xy equal to alpha plus beta. But guess what alpha and beta was? Alpha was log base b of x, and beta was log base b of y. And we just proved the product rule. And this is why all these rules work, right? I can go ahead and prove all of these, but to save a bit of time, we're going to move on to some practice. But that's how we know whenever we have a log with multiplication in the argument, we can split it up into simpler addition, two logs with the same base, and adding the two arguments separately. Same thing goes with division, turns into simpler subtraction. And the power rule says whenever we have an exponent in the argument, I can bring the power k down as the coefficient of the log. Let's put these rules into practice to retain this information. Let's take a look. Write the following logarithmic, that's hard to say, try saying it to yourself, logarithmic expressions as a single logarithm. Log 2 plus log 3. Now look back at what this is. It's the product rule, right? Log 2 plus log 3. So I can rewrite this, I can condense, I can combine these two logs into one single log. I can rewrite it as log of 2 times 3, giving us log of 6. Now, when we added the two logs, we multiplied the arguments. And keep in mind, we can only do this with logs that have the same base. So for B, what do you think we'll do? In the chat, I want you to chat this one. Message in the chat, what do you think our next step here should be? This time, we have two logs, again with the same base, and two different arguments, 10 and 2. And this time, we're subtracting instead of adding. When we added two logs, we multiplied the arguments. So when we subtract, what do you think we'll have to do with the two arguments here for letter B? Log of 10 minus log of 2 in the chat. And don't ever be afraid to, just chat whenever, right? Chat as fast as you can, whenever you want. Or you can take your time as well. Here we have addition, right? We're adding these two logs and we multiplied the arguments. So when we subtract, what do you think we'll be doing? Instead of multiplying, this time will be, great Olivia, we'll be dividing. Awesome. log of 10 over 2, and that gives us log of 5. Beautiful work. All right, now letter C is a little different than letter A. This time we're still adding, but notice how we have coefficients lying around here in front of the logs. We cannot combine them until we put these coefficients of the logs back into the argument of the log. So this 2 I'm going to move back as the power of 3, and 4 as the power of 2. And since I'm adding these two logs, what operation can I perform within one log? Based off of what we did in A, what can we do when we add two logs? What is the operation we can use within the argument of just one log? When we added the two logs in part A, we multiplied the arguments. So we are going to go ahead and do that again. We have 3 squared times 2 to the 4th. 3 squared is 9. 2 to the 4th is 16. 9 times 16 is 144. So we have log of 144. We're going to do the same thing in letter D here. The same exact thing. The first thing we have to deal with are these coefficients. I'm going to move them up as the power of the arguments. So I'm going to rewrite this first. Log of 3 to the 1/2 minus log of 4 to the 1/4. How can I rewrite 3 to the 1/2? In the chat. How can I rewrite 3 to the 1/2? I see 9 of us here right now. Anyone? How can I rewrite 3 to the 1/2? Don't worry about using the correct symbols in the chat. You can just type it out as well in words. That's the easiest way to do it. 3 to the 1/2. We talked about this earlier. Whenever we take a number to a fractional power, right, to a fractional power, like 1/2, I can rewrite it as the square root of that number. So here, 3 to the 1/2, what can I rewrite that as in the chat? Log of, we have 3 to the 1/2, that'll be, I see a lot of us are super shy, even though we're online. We have radical 3 minus log of the 4th root of 4. Now, since we have minus, we can divide, like Olivia mentioned earlier. So we have log of radical 3 all over the 4th root of 4, and boom. We have condensed this kind of disgusting, gross-looking expression into just one simple expression. Let's try E together. Again, I have coefficients in front of the logs. I'm going to be putting them as powers, just like this. So I have log of a squared plus log of b to the 5th minus log of c cubed. Now, I'm going to start from left to right. I know that these two logs are being added. So what operation can I use with the arguments? If I'm adding these, what would happen if it was to the power of 7/8 or 12/13? Great question, Kanav, and I'll answer that right now. If we have x to the 7/8, by exponential properties, I can split this up into x to the 7th and 1/8. Since I know a power to another power, I can multiply those two powers, right? 7 times 1/8 will be 7/8. I can also rewrite it as x to the 1/8 to the power of 7. This one I would rewrite as the 8th root of x to the 7, and this one I would rewrite as the 8th root of x to the 7th power. Now, for me, I prefer this one, but depending on what x is, it might be easier to do the 8th root of x and then simplifying that number first and then taking it to the 12th power. Did that help, Kanaf? Great question. Right now we're working with really simple fractions. So you might have wondered, oh, what if the numerator is not 1? And maybe that's why you asked that question. Good question. So now back to our original question. Awesome. I can multiply these two logs. I'll get a squared times b to the fifth. But I still have this minus log c cubed. And since I'm subtracting these two logs with the same base, I can divide the two arguments, and that would be my final answer. Same idea for letter F. But letter F, this one becomes a little more interesting, because once we have all these logs, I can combine the first two logs. This will become log of x squared times y cubed minus log of x squared y. And I can divide the two arguments. I'll have x squared y cubed all over x squared y. In the chat, does anyone notice anything we can do with this answer? Can we leave it like this, or is there more that we can do here? Log of x squared y cubed all over x squared y. Anything else we can do here? I see all your gears running in your brains. Trying to think, it's getting late. It's 6:30 p.m. Pacific time, 9:30 Eastern time. Trying to stay awake. Had a long day. It's only Tuesday. But we can simplify here, right? X squareds cancel. This 3 can turn into a 2 because it cancels out with one of the y's in the denominator. And so our final answer will be log of y squared. And that's it. Now, we've learned to condense. Now let's learn to expand. Go the opposite direction, right? Go do this vice versa. So we notice that these operations here are multiplication. So I can rewrite this as log base b of x squared plus log base b of y plus log base b of z cubed. But I'm not completely done, because I was asked to expand the following in terms of log base b of x, log base b of y, and log base b of z. Right now x is squared and z is cubed. So I can use our power rule for logarithms and move these powers down as the coefficient of the log. So I have 2 log base b of x plus log base b of y plus 3 log base b of z. And that would be our fully expanded log. Now let me ask you in the chat, I have x divided by y cubed in our argument. What operation can I rewrite that as if I were to split these up into 2 separate logs? Log base b of x and log base b of y cubed. What would go in between these two logarithms? Now having solved at least, 8 to 10 questions, right? Using the product rule, quotient rule, power rule, what operation would go in between these two logarithms? Knowing that this time we have x divided by y cubed. X divided by y cubed. Going back to our quotient rule, subtraction. Great, Olivia. That's amazing. Yes, that's correct. Subtraction. Whenever we have division in the argument of a log, we can rewrite it as 2 separate logs with a subtraction in between. And this time, x, we're good. 3 is a power. We want to move it to the front of the log as the coefficient. So now we have log base b of x minus 3 log base b of y, just like that. We're going to do the same thing here, but we're going to skip some steps. Here we have a multiplication and a division. So I can rewrite these as log base b of x, log base b of radical y, and log base b of z. And now fill in the operations. What is the operation that will go in between these first 2 logs here? What will go right here between the x and the radical y? We know that they're being multiplied within the argument of the log. So what operation will go in between the logs here? Maybe what it is that the chat could be about 10 to 15 seconds lag from my stream. So I'll wait a couple seconds for everyone to have an opportunity to respond. So far, it's just Olivia and Kanav. Great, Olivia. Yes, this time it is addition. And because we have the division bar between x and radical y and the z, we will have a subtraction in front of log base b of z. Awesome work. Now, radical y can be rewritten as y to the 1/2. So if I were to rewrite all of these as separate logarithmic expressions, I would have log base b of x plus 1/2 log base b of y minus log base b of z. Now, for letter D, we have log base b of x over b to the 4th. This time, since we have, again, a division, we will have subtraction in between. Now, we have something really interesting this time. We have log base b of x, and we have the minus 4 log base b of b. This is the first time we've seen the base of the log be the same as the argument. Let's think about what that would be. If we have log base b of b equal to some box, that means b to the power of box is equal to b. What is box equal to then? Any number to what power will equal itself? In the chat. Any number to what power will equal itself? B times itself, how many times will equal b? Great, Kanav. 1. 1 is correct. And so therefore, this entire logarithmic expression right here will equal 1. So our final answer here will be log base b of x minus 4. Because 4 times 1 is 4. And that when we're done. Awesome work. All right, now we have some practice that we can do. We're going to practice converting these logarithmic equations into exponential equations to see if we can solve for the unknown value of x. So for letter A, I can rewrite this logarithmic expression, log base 3 of x equal to -1 as 3 to the power, 3 is the base, to the power of -2 is equal to the argument of x. Now, from everything that we learned today thus far, how can I rewrite, or in other words, simplify 3 to the power of -2? I know that 3 squared is 9, but that's not the same as 3 to the power of -2. What would x equal here? We have a negative power this time, a negative power. We know 3 squared is 9, but because we have a negative power, we flip that 9 to the denominator, and we get 1 over 9. It looks like we are struggling a little bit with exponential properties, but don't worry, in my Algebra 2 course, this logarithmic properties comes after exponential properties, and so we'll for sure reinforce those skills, fill those gaps. You should have learned this in Algebra 1, but it looks like we are filling some gaps today. Don't worry at all. We're going to be filling those gaps and reinforcing those skills before we get to logarithmic properties again in my course. All right, let's take a look at letter B. So for the rest of these problems, I'll try to model because it does seem like exponential properties is a pain point for everyone here today. All good. So we have 9 to the power of 3/2 is equal to x. Now let's split up this 3/2 as two separate powers. We have 9 to the 3/2. That would be equal to either 9 cubed to the 1/2, because we know 3 times 1/2 is 3/2, or we can rewrite this as 9 to the 1/2 to the power of 3. Which one is easier? Well, let's think about it. 9 cubed gives us a really big number. I don't really want to work with that, whereas 9 to the 1/2 is a lot easier. That gives us the square root of 9, which is 3. And so 3 cubed is just 27. So a lot easier, right? So x is equal to 27, just like that. If we did it the other way, we would have gotten, I believe, 729 to the power of 1/2, which is the square root of 729, which is in fact 27. Next one. I believe we can try this one. X to the power of 2 is equal to 16. Everyone in the chat, what is x equal to here? If x squared is equal to 16, x is equal to what number times itself gives us 16? Surely we know this one. Great, Olivia. Great. Olivia says 4. Any others? This is a freebie in the chat. Just type in 4. X is equal to 4. Now, usually we would say x is equal to positive or negative 4 because when we take the square root, we have to consider both the positive and negative values. However, for a logarithm, the base of the logarithm must always be positive. And that's why in this case, we only have to consider the positive value of x. Great. Next one. The base x to the power of our power, 1/2, is equal to our argument of the log, 1 over radical 3. Now, x is to the 1/2. So we can rewrite that as radical x is equal to 1 over radical 3. Let's think about this for a second. That would mean x has to be 1/3, right? Because if x is equal to 1/3 and we take the square root of both sides, the square root of x would be the square root of 1/3. But whenever we have the square root of a fraction, we can take the square root of the numerator and denominator separately. Again, exponential properties. The square root of 1 is 1, and the square root of 3 is the square root of 3, and that's how we know x is equal to 1/3. Alrighty. Here are some applications. Logarithmic properties are assessed very often, and especially if you're here for Algebra 2 today, that means you have maybe already taken the PSAT, maybe preparing for the SAT or ACT, and oftentimes Algebra 2 isn't even really assessed on the SAT, but it can be very, very useful to know. On the ACT, you will definitely see logarithms. So for every lesson that I do in Algebra 2, I will always end with some type of challenge problem or some type of application problem that will help you do well on these national level exams, standardized tests, and things like that, exam style questions. So given that A, B, and C are all positive, find an equivalent expression to log of this argument. This looks really familiar, right? Earlier we worked with X, Y, and Z, but in my course, you'll be getting really familiar with many different types of variables because once you get into pre-calculus, once you get into physics, once you get into chemistry, you are dealing with so many different types of variables, not just confined to X, Y, Z, right? So we're working with A, B, C here. We know that A and B to the 4th is being multiplied and C is being divided. So let's first rewrite these as individual logs and think about what is the operation that will go in between each of these. So in the chat, between log of A and log of B to the 4th, what is the operation that will go in front or in between these two logarithms? We have A times B to the 4th. So this time we have multiplication between two terms, A and B to the 4th. So when we split the argument inside the log into separate logs, multiplication within the argument can be rewritten as, I know Olivia already knows it, but anyone else in the chat, don't be shy. Multiplication within the argument of a logarithm would be addition. Therefore, division within an argument of a log would be subtraction when we split these logarithms up. Last but not least, we must use the power rule to completely expand. So we have log of A plus 4 log of B minus log of C. Now this next problem is straight from the SAT. It's actually straight from an SAT math section within the last 3 years. And the SAT is administered, I think, something like 10 out of 12 months in a year. So this is coming up pretty often now. Log of x is equal to 2 and log of y is equal to 3. So think about this. We're trying to expand this logarithm into log of x and log of y. So let's do that first. Ignore the 2 and the 3 for now. Log of x to the 5th times y will give us log of x to the 5th plus log of y. Now don't get confused with this 5. This 5 will come down as the coefficient of the log. So you have 5 log x plus log of y. And good thing we didn't get distracted by these 2's and 3's, because all we need to do now is substitute them in for what we have left. We have 5 times 2 plus log of y is 3, and we get 13 as our final answer. And that was the correct answer on this SAT math question. All right. If you're still here with me, very easy thing to do here. Put a plus in the chat if you learned something new today. Put a plus in the chat if you learned something new today, or maybe a W if you thought it was a W lesson. And while you do that, call your parents or your guardian over, or any adult that's close to you over. And I'm so excited to share this special news with you. Our lesson may be ending, but your progress does not have to. My EdSpace Algebra 2 full year course will start on October 6th. And each course will include 2 engaging live and interactive lessons, just like what we had today, every week. So twice a week, we'll be meeting twice a week until the beginning of June. So for over the course of 8 months, a total of 60 live lessons. Every lesson will be video recorded, including this one. We're currently recording this lesson so that if you missed a part of it, you can go back and review it. And guess what? This particular lesson as well, if you learn logarithms, let's say next week in class in school, you can come back to this and review and look at all these exam style questions to reinforce your skills and fill the gaps as well. Or if you have any extracurricular activities and you can't make it to the lesson, you can check out the recording and the chat as well. You'll have professionally designed workbooks for every lesson, just like you got today. In the video description, you'll see the workbook that you could have utilized, or hopefully you utilized today to jot down all your notes, and you don't have to frantically, copy down the question, because oftentimes in school, you'll be copying down a question, but the teacher has already started solving the question, things like that. Or you're just, letting time pass by copying down the question. We don't like wasting time like that in my course. After every lesson, you will get 5 practice exam style questions. Just 5 practice problems, but exam style. And the way this works is that you're not getting an answer booklet in the back of your workbook or anything like that. You'll get detailed video solutions made by me. Like you see me on this screen, I'll be solving the problems by hand on the screen to show you exactly how I would solve this problem. I'll show you a long way of doing it. I'll show you the quickest way of doing it, and just exam tips and tricks, things like that in these detailed video solutions. But how much is it? That's the big question. For context, when I used to be a private tutor, if you'd like to guess in the chat, how much do you think I used to charge per hour? And as a refresher, I used to private tutor any grade level from grade 6 math all the way to students preparing for graduate school or in graduate school. I've taught college calculus, all that in between. So I used to charge a minimum of $100 per hour up to $200. Yes, Kanav, you were here last time. Welcome back. And the big thing here is that families often have to choose between what works and what they can afford when it comes to private tutoring. You'll never find a tutor that's like $20 an hour and effective. And you'll never find an effective tutor for that cheap either. And that's why we created My EdSpace. We wanted to create affordable, accessible lessons and tutoring style streams so that every student can access the highest quality of teaching. And all this, everything that I mentioned so far, for just $99 a month. And that's approximately 7 to 8 lessons per month, running from October 6th all the way through June 5th. 8 months, $99 a month. That comes out to a total of $792. However, because you are here today, you'll get a 20% additional discount on our annual package. So that $792 becomes $649. That's less than $11 an hour, which is absolutely insane. But that's what we believe in. That's why we created My Ed Space. We want to create accessible, affordable, effective, high quality education in a high tech space as well. And to protect you from any risks, we provide a 30-day risk-free full refund guarantee. It is first come, first serve. This is a limited time offer. So if you are interested, text me, code word START to this number, 512-900-1283. And if you don't want to make any mistakes with the phone number, you can scan the QR code on your screen. It will automatically prompt you to text that code word to my number. I have a couple minutes here left for a Q&A, so if you have any questions, feel free to ask. I will be here. But otherwise, thank you for being here. I hope you enjoyed the lesson today. I hope you learned something new, and I hope to speak with you in the chat or via text. Thank you, everyone, for today's stream. Thank you for being here. Have a great rest of your evenings.